Good morning, everyone. I am Muskan from BSc Chemistry Honors 3rd year. Today I am discussing the vibrational rotational spectroscopy of Pradeep's Physical Chemistry Volume 3. Pure vibrational and vibrational rotational spectra of diatomic molecules. Vibrational energy levels of a simple harmonic oscillator. A simple harmonic oscillator is the one in which the restoring force is proportional to the displacement in accordance with Hooke's law, such as F is equal to minus kx, where k is called the force constant. For such an oscillator, the potential energy is given by half kx square, and this is the equation for a parabola. Hence, a parabolic potential energy curve is obtained as shown in this figure. Using the concepts of quantum mechanics, it can be seen that if the vibratory motion of the nuclei of a diatomic molecule is taken as equivalent to that of a simple harmonic oscillator, then the vibrational energy is given by this equation, where mu is the frequency of vibration and mu is the vibrational quantum number with allowed values of 0, 1, 2, 3, etc. Putting mu equals to c by lambda, that is c mu e dash or c omega e star, where mu e bar or omega e represents the equilibrium vibrational frequency in the terms of wave numbers, and it can also be written as like this. Putting mu equals to 0, 1, 2, 3, etc. in the equation number 4, it may be seen that the vibrational energy levels of harmonic oscillator are equally spaced. These are shown diagrammatically in this figure 3.23. For the lowest vibrational level, mu equals to 0, and the energy for this level will therefore be half hc omega e. This is called 0 point energy, and it implies that even at absolute zero, when all the translational and rotational motion ceases in a crystal, the residual energy still remains, the vibrational motion still exists. Now the selection rules for the vibrational transitions in a simple harmonic oscillator. The gross selection rule for a molecular vibration is that the electric dipole moment must change when the atoms are displaced. Here, note that the molecule need not have a permanent dipole. Based on this, the specific selection rule for the vibrational transitions is change in the vibrational quantum number should be unity. Transitions for which delta mu equals to +1 correspond to absorption, and those with delta mu equals to -1 corresponding to emission. Vibrational spectra of a simple harmonic oscillator. Applying the selection rule, as the transition can take place between the vibrational levels whose vibrational quantum number differ by unity, the energy absorbed by a diatomic molecule, taking it as a simple harmonic oscillator when the transition takes place from mu to mu +1 level, will be given by this. Thus, only one absorption line will be obtained in the vibrational spectrum whose wave number is equal to the equilibrium vibrational frequency of the diatomic molecule. Otherwise, too, as the vibrational levels are equally spaced, any transition from any mu to mu +1 will give rise to the same energy change, and hence only one absorption line is expected. Further, at room temperature, as most of the molecules are in the lowest vibrational level with mu equals to 0. Therefore, the transitions taking place are from mu 0 to mu is equal to 1. The frequency thus observed is called the fundamental frequency, and these spectra are observed in the IR region. Types of molecules showing vibrational spectra. As already mentioned, the gross selection rule for a diatomic molecule to give a vibrational spectrum is that the dipole moment of the molecule must change when the atoms are displaced due to the vibration. The condition required is only the change in dipole moment, and the molecule need not have a permanent dipole moment. For example, in the case of homonuclear diatomic molecules like H2O2 and 2, which have only stretching motion and vibrations and no bending motion vibration, the dipole moment does not change during the vibration. Hence, these molecules do not give the vibrational spectra. They are said to be infrared inactive. On the other hand, heteronuclear diatomic molecules and the polyatomic molecules like CO2, H2O, which show change in dipole moment, give the vibrational spectrum. Vibrational energy levels of an n-harmonic oscillator. When a molecule is undergoing any simple harmonic oscillation, the restoring force of the harmonic vibrations is directly proportional to the displacement, and the energy of the harmonic oscillator is given by this, where mu is the vibrational quantum number, which may be 0 or an integer, and omega e is the equilibrium frequency of vibration of the oscillator, such as for small displacements. Selection rules for the vibrational transition of an n-harmonic oscillator are: whereas the selection rule for harmonic oscillator is delta mu equals to plus minus 1, the selection rule for n-harmonic oscillator are plus minus 1, plus minus 2, plus minus 3, and so on. Thus, all type of vibrational transitions are possible. However, the transition from mu0 to mu1 is found to most intense and is called the fundamental absorption. The transition from mu0 to mu2 has a very weak intensity and is called the first overtone. The transition from mu0 to mu3 has still weaker intensity and it is called the second overtone, and so on. Now the vibrational rotational spectra. Pure vibrational spectra are obtained only for liquids where rotational motion is hindered due to the interaction between the liquid molecules. However, in the case of gaseous molecules, as the energy required for rotation is much less than that required for vibration, the vibrational motion is always accompanied by the rotational motion, and hence we do not have a pure vibrational spectra. Instead, we have a vibrational rotational spectra lying in the infrared region. As rotational motion and vibrational motion takes place independent of each other, applying Born-Oppenheimer approximation, the total energy of the molecule may be taken as the sum of the rotational and the vibrational energy. Thus, it can be written as E total equals to ER plus E mu. And expressing it in the terms of wave numbers, it can be written as like this. But from equation number 4, section 3.15 and equation number 2, section 3.26, mu j equals to bj into j plus 1 and mu v equals to mu plus 1 by 2 omega e minus mu plus 1 by 2 whole square x e omega e. Substituting these values in the equation, we get bj into j plus 1 plus mu plus 1 by 2 omega t minus mu plus 1 by 2 ka whole square x e omega e. Here it represents the wave number of rotational level with quantum number j in the vibrational level with quantum number mu. From equation 6, it is clear that same vibrational level there will be a number of rotational level corresponding to the j. When a transition takes place from a level with quantum number mu and j to a level with quantum number mu dash and j dash, the energy change expressed in the terms of wave numbers will be given by delta mu bar equals to this. And restricting to the transition from mu 0 to mu dash equals to 1, we get b into j dash minus j plus d dash plus 1 minus 2x e omega e. And put 1 minus 2x e omega e equals to omega naught, we can write it del mu naught equals to the omega naught plus b j dash minus j into j plus j dash plus 1 for transition with delta j plus 1. Delta mu bar equals to omega naught plus 2b into j plus 1, and for transition with delta j minus 1, delta mu bar equals to omega naught minus 2b into j dash plus 1. Combining these equations, we get delta mu bar equals to omega naught plus 2bm. Now the PQR branches of the vibrational rotational spectra. In the equation, omega naught represents the fundamental frequency. This is called the center or origin of fundamental. For delta j minus 1, it is called the P branch of the spectrum because these lines with the frequency lower than the fundamental frequency and the lines with frequency greater than fundamental frequency, then these lines are called R branch of the spectrum. And for delta j equals to 0, when a vibrational transition occurs without accompanied by rotational transition. A single line should be obtained at the center. In actual practice, as the rotational constant of two vibrational levels are different, a cluster of closely spaced lines appear at the center, and this group of lines is called the Q branch of the spectrum. Intensities of lines. It is important to note that intensities in P and R branch of the type shown in this figure will be observed only if the resolving power is very high. If it is not high, then the spectrum observed is as shown in the figure 3.26. This is the spectrum, and the PQR branches are shown here. Structural information: by carefully locating the band center corresponding to the transition and the transition, the value of frequency omega E and n harmonicity constant can be obtained. Also, the frequency separation between any two adjacent lines gives the value of 2b, and we can calculate the moment of inertia and bond length. As discussed in the rotational spectra, the frequency separation, knowing it, the moment of inertia and hence internuclear distance can be calculated. Calculation of force constant: taking the simple case when a diatomic molecule may be considered as a simple harmonic oscillator, an oscillator in which the restoring force is directly proportional to the displacement in accordance with Hooke's law. We have F equals to minus kx, where x is the displacement and it is equal to the distance to which atoms have been stressed, minus equilibrium distance between the atoms. X equals to r minus re in the equation 13 is called the force constant. If x is equal to 1, k equals to minus f. Force constant may be defined as the restoring force per unit displacement. Omega E equals to 1 by 2 pi k by mu ki power 1 by 2, where mu is the reduced mass, and to calculate the k, it can be rewritten as follows, where m1 and m2 are the masses of oscillating atoms. Thus, knowing vibration frequency omega E and the masses of the atoms of the diatomic molecule, the force constant can be calculated. However, a problem arises with the polyatomic molecules because each bond has a different force constant, and it is solved by assuming that a force constant is associated not only with every bond but also with every bond angle. Thus, the multiplicity of the bond can be predicted from the value of the force constant. For example, the force constant for carbon monoxide is 18.6 into 10 raised to power 5, whereas for the carbon double bond in carbon dioxide is 15.2 into 10 raised to power 5 dynes per centimeter. This result confirms that CO2 has resonating structures containing both carbon oxygen double and triple bonds. We can write it also as like this. Thank you so much.